Yeah, that's like butter usually. It's not butter, it's butter.
All right. Like I said, you say jump, I say how high.
It's kind of tough, but I don't like nuclear waste.
Hey guys. All right, we're gonna get started. So today, Charlie's going to be talking about parallel algorithms for asymmetric read-write costs.
So as usual, the introduction stole sort of some of my thunder here. But I do get to tell you that I worked with a whole bunch of people on this cool project. And we recently had a paper in SPA 2016. So if you like what I'm talking about and want to get more details, you can either talk to me more offline or go read that paper. It's great. So the basic premise for our work is that there is a new wave of memory technologies being developed. And they have some really interesting and useful properties. One, they're non-volatile, which is great for main memory because it means when your main memory runs out of power, you get to still keep all your data. You get a lot more system resiliency, a lot more fault tolerance, good things. It's byte addressable, so you can talk to whatever byte you need to talk to. It's got a lot better performance properties than Flash. You can see those listed there. And then compared to DRAM, it's got less idle power and great storage density. So it has a lot of good properties, and a lot of systems architects are working on putting this into their architectural designs, and it's already available for disk replacement style storage. But it does have one really interesting property from a theorist's perspective, and that's the asymmetry between reads and writes. So writes take a lot more time, energy, bandwidth, etc., you name it, than reads do in this memory technology. And that's because the way it works is to read something out of this system, you put some current, some voltage across it, and then you read the current. If it's in one state, it's got a high resistance, you read a low amount of current. If it's in the other state, it's got a low resistance, you read a high amount of current. But in order to write data to this memory, you need to actually change the state. So you put a lot of power into it, you heat it up, and then you let it cool down either really quickly, which I believe gives you the amorphous phase, or slightly more slowly and controlled, which gives you the crystalline phase. So that part of the talk isn't particularly important, but hopefully you found that a little cool explanation. The important part here is the difference in the read costs and write costs. And we're going to model that difference where a read has unit cost and a write has some cost parameter omega that we can take in as a system parameter. So why does this matter? It turns out that this matters for most algorithms. Say you have a problem that you want to solve and you have limited resources. You're going to do the best you can with 1 watt of power. And you have 2 different algorithms you're looking at. One of them takes 100 reads per input and 100 writes per input. And the other one takes 200 reads per input and 50 writes per input. It turns out, when you do some analysis on this, even though the second algorithm does more total work, you can do twice as many entries with the same amount of power using this algorithm. And that's because of the asymmetry in reads and writes. So now we have to go back and take a look at all the algorithms we've been essentially working with for all of algorithm design, where we assume reads and writes are the same thing, because that assumption is no longer true. So there's been some other work in this area. There's been a lot of people who work on NAND flash and algorithms for NAND flash, or ways to efficiently schedule where you write data on NAND flash. But there are some differences there, because with NAND flash, it's not necessarily byte addressable to make changes. You have to clear an entire block at once. There's also been some work in database query processing. The asymmetric memory has gotten to disk-level systems much more quickly than it's gotten to main memory systems. So the database people have been working on this for a little while. But they've been primarily working under database design analysis and with database algorithms. And then, of course, you've got the architectural people who are the ones actually pushing this thing, putting it into their architectures and saying this is great and you should all get ready to use it. And then in addition to our work, there's been a few papers out of let's see, I think it's UC Berkeley, it might be Stanford, I always get those two mixed up, where they talk about communication avoiding algorithms in distributed systems, and they model read-write asymmetry in that distributed system. So in SPA last year, we started to look at this problem and provided a few basic models that might help us figure out how to solve the problem. And then we provided some sorting algorithms that work well in these models. So if you remember, our omega is our read-write asymmetry parameter. So we were able to get these results on the asymmetric RAM, asymmetric PRAM, and asymmetric external memory models.
Why can't you just read the whole input, sort it, and then write the output?
So because
in order work time seems to say. Right, you read everything, you sort it, and then you write out.
I think you don't have access to other memory?
Yeah, so that's essentially what we were able to do, but it's not quite that simple, because in the asymmetric RAM model, every write costs you omega. So there are ways to do sorting where you only do O of n writes, and the paper goes into more detail on that. One simpler way to do sorting with only n writes is to take everything and insert it into a binary search tree that you build as you go along. And then with high probability, you're only doing O n writes. There are some other ways. We do some merge sort with particular breaking methods. But I would refer you to that paper for that. That's not quite as relevant to the details of this talk. So if we already have these, you might begin to ask yourself, what else is there to do? It turns out that when we look at this particular example, we can see some things that aren't great about the current models. So say you want to do a typical reduced task, and you want to do it in parallel. So you're looking at the asymmetric PRAM model. Now we have our generic reduced code over here. This is high level. This is not implementation.
So what is asymmetric PRAM model?
So the asymmetric PRAM model is a model we discussed in a different paper. Essentially, it's like the PRAM model, except all of your writes cost omega.
What's PRAM model?
Everybody
else knows that, just I'm not asking.
Everybody else knows.
Okay, good.
Except maybe.
So abstracting that away for a second, and assuming that we can just arbitrarily do things in parallel,
Okay.
our reads cost 1 and our writes cost omega. When we look at this reduced code, then each split is going to take O of omega work, because we have to write out something for this reduced function of the smaller input. Now, again, this is high-level code. We'd be doing these in parallel. So our work, we're doing 2 of the same thing plus O of omega work. Our span, we're doing 1 of the same thing, since they're 2 in parallel, plus O of omega work. So we get these nasty little omega terms on our total work and span in the result. And we would like, since this is actually only doing 1 write that the caller ever has to see, something where these omega terms are additive instead of multiplicative. Because it's really trivial in this new model to get algorithms where you just take your cost, you multiply it by omega, and you say you're good. But that's a lot of extra overhead that we'd like to avoid. So think about this, keep this in mind, and we'll come back to this discussion once we've seen some of the details of the asymmetric NP model. So the asymmetric nested parallel model, or asymmetric NP model, is what we're going to be talking about. And then in addition to defining this model, our paper talks about a whole bunch of algorithms. Now, unfortunately, I don't have time to talk about a whole bunch of algorithms. So I'll be briefly discussing tree contraction as an example of how we apply our model and some of the unique techniques in the paper. But if you want any more details about these, again, talk to me offline or read the paper.
So what is the reduction of rights column? Reduction relative to the naive?
Yeah, so this is relative to taking the state-of-the-art algorithms and just running them on the asymmetric model, where essentially every write costs omega. So for almost every algorithm, the state-of-the-art algorithm's cost is just going to be omega times its cost in the symmetric model. So, the asymmetric model. We're going to be breaking this down into 3 parts. Our model of computation, our memory model, and how we handle scheduling on the model. So first, we're going to be doing our model of computation. This is the same as the nested parallel model. So anyone who knows that, you can sort of tune out for this little bit. That's OK. For anyone who doesn't, I'm going to be covering that. Hopefully, it won't be too slow for any of you. So any amount of sequential computation, for example, this function here, we represent as a node. And we're going to use these nodes to build a directed acyclic graph, or a DAG, that represents the parallel computation we're interested in. It turns out you could represent a sequential computation the same way, but it's just one node, so it's not particularly interesting. When you have parallel computation, you create that parallelism using a fork join construct, where you say fork join with 2 snippets of code, and those snippets of code are run in parallel. So when you convert that to your DAG representation, you have your parent node, which splits into 2 child nodes that are on the same level of the DAG. And then once those 2 child nodes have finished their work, they combine back into the parent node. You can sort of think of this as parent prime. And while these 2 children are running, the parent node is sort of suspended in the background. So now we're going to talk about the memory model. So if you remember back to the first slide, I had this interesting picture from Intel that shows approximately what their architecture is going to look like in some reasonably near future. It turns out our memory model maps pretty well onto that architecture. We have our CPU, which is going to be many CPUs in this particular case. So that's your processor, however you want to abstract it. And every instruction that the CPU does has unit cost. There's also a small symmetric memory for each CPU. And that memory is stack allocated and of constant size, or limited size. We'll talk about exactly what size in a second. And then the asymmetric part comes in with the large memory. So we're assuming that this is an infinite size memory that all of the processors can talk to. And this is how they communicate with each other. And that's heap allocated. So the cost bounds for these memory models are shown here. So the CPU can talk to its stack memory very quickly, efficiently. It can read from the heap fairly easily. But whenever it tries to write new data to the heap, it costs omega, which is our read-write parameter.
At the risk of asking another question, I'll bring also answer to. So what's the point of a model? What's the difference between the stack model and the heap model, like as far as the access to the memory model?
So it doesn't really affect how the algorithm works. It's just sort of a conceptual thing. If you're thinking about running this as a Java program, this is going to be the stack for each of your function calls.
So as analysis of algorithms, this word stack and heap make no sense difference.
Correct.
Okay.
But it is a detail of the paper, which is why I mention it. And if you were to try and implement something that closely mirrors this, it might become a relevant detail. So I promised you I was going to tell you more about the size of the stack memory, and we're going to do that now. So we have 2 different categories of nodes for the stack memory. Non-leaf tasks, which are any task that has a fork call inside of it, get some constant amount of stack memory. So that's O of 1. And then all the tasks that don't have tasks inside them we refer to as leaf tasks, and they get some memory ML, which is another parameter of the system. The other interesting part here, and why we call it the stack memory, is that each node has access to the stack memory of itself and all of its ancestors in the DAG. So for example, task C can access its stack memory, A's stack memory, and root's stack memory. Similarly, D can access D, A, and root. And this becomes an important point later as we get to the scheduling.
I'm not sure I understand the picture. So the root forked A and B?
Yes.
But then, like, I don't understand how B was forked by two guys. I mean, somehow.
So no, the root forks A and B, and then A forks C and D, and B doesn't do any forking.
They're doing joining as they're coming back down. Okay,
so
gotcha.
once C and D finish, they come together and restart task A. And then once A and B have finished, they restart the root task.
So the reason you highlighted this green part is because it's the maximum memory which is possibly allocated by the algorithm.
So this is just pointing out all the leaves. So yes, technically, for this particular computation, this is the maximum amount of memory allocated by the algorithm, ML times the width here. And more generically, you could look for similar cuts in the DAG, but we don't discuss that as much in this talk.
Why does it make sense to have access to all of your ancestors' stack memory?
So that helps interprocessor communication. So say I'm a node and I'm working on something, and I want to delegate some amount of work to my child. So what I can do is I can create a variable in my stack memory that says, here is your input parameter, go work on this. And then I fork and I create a child. And that child says, all right, what's my input parameter? Let me go read that from the stack memory above. So it allows you to transfer variables down this line to the children.
So access to parents' memory is read-only.
No.
But then there's some common memory that everything has access to, so eventually.
Yes, so that is something that can happen. And we're going to talk more about that in the scheduling portion. So everything can access the stack memory of the root, which is why it will potentially no longer become stack memory. Any other questions on this before I continue? All right, so now we're going to get into the interesting stuff, the scheduling and why we made some of the decisions we made in our model. So the nested parallel model uses work stealing to handle scheduling of the jobs it has. And we continue to use a modified version of work stealing for the asymmetric nested parallel model. For those of you who don't know how work stealing works, I'm going to go through a brief example. So say we are a scheduler and we're starting a computation, all we know is the root. So we take one processor and we put the root on it and we give it a deck of things to work on. So the processor starts working, it finishes computing the root, and then discovers, because the root forks, that there are now tasks A and B. So it takes the left child, in this case A, and starts working on it. And then the right child gets added to the bottom of the deck. I forgot to explain what a deck is. Deck is a doubly ended queue. You might also hear it pronounced DQ. I don't know which is the proper pronunciation, but I'm going to use deck for this talk, and hopefully it doesn't make anyone too upset. So we take the right child, we add it into the bottom of our deck here, and we continue processing. So at some point we finish A, we go through, we start working on C, we add D to the deck, and everything is great. And then once you finish something that doesn't fork, you don't have anything else to add to your deck, so you take the bottom item off your deck and you start working on it. Then this finishes, we repeat the process again until we finish the computation. Now, this is if we only have one processor working on this particular problem. If we have multiple processors working on this problem, what can happen is processor 1 is starting the computation, it's chugging along, it's completed root, it's completed A, it's working on C, and its deck looks like this.
So what are the letters to the left of the job letters?
So these are the parents that spawned these tasks. So this becomes useful in the original proof of work stealing. You can sort of ignore those for now. So processor B is also assigned to work on this job. And processor B is like, hey, I don't have anything to do. So it picks another processor assigned to this job randomly, and it goes to the deck, and it steals the top thing off the deck if there's anything there. So then that item goes into B's processor, and B starts its own deck, working on exploring the graph in the same way A does. So in order for that to happen, processor 2 needs to know the stack data for B, which means it needs to know the stack data for B and all of its ancestors. So this leads us to the question of how are we going to handle that communication? So if we look back at our model, the way communication between processors happens is you have some stuff in your stack memory here, and you wanted to get it to this processor over here. So what you have to do is you have to first write that data out to the heap, and then have the other processor read that in. So we want to figure out an effective way of doing that work-stealing communication between processors that doesn't cost us too much. So the first thing you might try doing, sorry, I started talking ahead of my slides here.
So what do we store in a heap now?
So
This is a heap now is external memory.
yeah, so the heap is the asymmetric memory that's this large thing that everyone can access.
Yes. And
So we haven't put anything in there explicitly yet, but if you are processor 1 and you're trying to send data to processor 2, the only way you have to do that is to write your data from your stack into your heap.
Oh, so the stacks are not shared.
Correct. They are not shared between processors. They might be shared between nodes, but nodes and processors are different. So if we go back to our example here, processor 1 can do all of this. And all of the stack memories from all of these nodes will be on processor 1 until processor 2 comes in and makes this steal and takes this data. Then this stuff will be on processor 1, and these things will be in the heap and therefore accessible to everyone.
What are we keeping in the heap right now?
So at this particular point in time, we have the stack memory for B and the stack memory for root in the heap, plus any data that these nodes specifically allocate in the heap.
So you can assume the heap to be the main memory and the stack memory to be the private cache for each processor. So you have some registers, but you cannot do everything, and the other processors cannot access your registers.
All right, have I clarified everything? All right, excellent. So our communication model, fairly straightforward. If you want to send something to another processor, you have to write it out to the heap. So now we need to decide how to get the things that are stolen from processor 1 to processor 2 efficiently. So one important thing to note here, and the reason we made this decision comes up in a second, is that all of our non-leaf stacks are O1 sized. So that means that the things we have to move over are very small, if we can limit the number of them that we have to move. Sorry, that's not supposed to be there. So approach 1, naive approach, just write everything out to the heap. That way everything has access to it. You never need to worry about moving data on a steal. So here is a problem example for that case. We have our basic computation here running on processor 1. Processor 2 comes along and steals B. So in this situation, you've written everything out to the heap. So you have all of these things in the heap. So you have your stack memory for root, stack memory for A, B, C, and D. Turns out you don't want all of that. What you really want is the stack memory for root and B in the heap. It turns out with this naive approach, you have to pay a cost of O omega for each fork because you're writing out a stack frame to the heap. That's bad. So approach number 2, if we didn't work to write everything out immediately, why not write it out lazily? Just wait until a steal happens. Turns out there's some difficulty with this too. So we're going to look at this example this time. And processor 1's chugging along. All the green things are things that processor 1's completed. Processor 1 is working on G, and it's got H and B in its stack. Processor 2 comes along and wants to steal. All right, that's great. We steal B, so we write out B, we write out the root. Everything's fine. Now, processor 3 comes along, and processor 3 wants to steal something. So processor 3 steals H. Now, we have a lot of stuff to write out. And it turns out, when you're along these right spines of things, you can have a lot of stuff to write out. And that means that your work stealing can take a lot of time. And it turns out the scheduling proof for work stealing depends on this amount of time that it takes to do steal being bounded. So we'd like to come up with a way to bound that time. And it turns out you can do that with a fairly simple transformation. So if we have our original computation DAG here, we can change it by converting every fork in the original DAG into 2 forks in our new DAG. The first fork creates one child that actually is going to do work, that we're going to call the forker, and one child that's just going to sit there and do nothing, the dummy. So the forker goes ahead and forks the child tasks that you actually want to get done in your original DAG, and the dummy just sort of sits here and does a no-op and then returns. And what that does is it means that you can never have a right spine in your resulting computation DAG. And therefore, you can never have to transfer a whole lot of data. Because if you...
What's the difference between left and right?
Yeah, I don't.
So it's sort of an arbitrary distinction where you're always working on your left child first. If you go back to our work stealing model. Another way to think of it, and the way that was originally done in the Lyserson proof, was a fork is your original task keeps running and performs the work of one of what I'm calling the children.
And that's the left one.
Yeah, and that's the left task. And then the other task is spawned in a new thread.
Okay.
So going back to our change here, this means that in order to steal C, a processor would first need to steal the dummy. And when you steal the dummy, then you have to write out A's stack memory. Question?
Can you say the same thing without introducing the dummy? The change the algorithm?
So you can set up your scheduler such that it you modify the stealing method to fail and write out one thing on a steal that goes a long way, but you're getting a lot into the details of the scheduler here, whereas this is a fairly simple transformation of the model that doesn't affect your cost bounds significantly. It is possible to do it by modifying the scheduler, but we believe that conceptually it's a simpler and more efficient idea to do it with this transform.
What you get by doing this is that you get to kind of parallelize the work of writing everything out, because different processors could be doing it. Because they just write out one thing, and then they fail, and they let other processors try to help. So you get like a parallelism going on.
Any other clear question?
The DAG you have, you assume that it's known, it's not dynamic? You can imagine a lot of algorithms that the DAG is going to be generated on the fly.
So you can generate this on the fly as well. So let's assume I know nothing but A.
So then the next question is, though, do you have a race condition where some task may get done more than once?
No, you don't. So the way this works is assume we know nothing but A. A calls fork. So what we do is we say, all right, well, fork is going to be slightly rewritten as this new thing that says fork this first task and the second task. The second task does a no-op and completes. And the first task forks into these two tasks that were originally passed to our fork from A. So your deck has this on top, then this, and then the processor working on this. So you have the same exact work stealing model where a processor goes in and sees one thing on top of the deck. So we're not actually changing that at all. So the first processor will steal the dummy, and then it will have the data get written out from the dummy, and it will work on the dummy, which in effect will take no time. And even if you have two processors go in and try and steal from the same time, that's the same as if you had two processors go in here and try and steal at the same time.
Okay, so but before even doing this transformation, so I think something I don't understand, so there's this work stealing model, and there's this abstract description of how it behaves with multiple processors, and you're basically describing the implementation of that with this memory, right? So the question is, what properties is that supposed to have when, in the work stealing model, two things are operating on the same memory, right? Because there's this shared stack that they have in the root. So two processors could conceivably both try to work on the same bit at once. And then what properties is this implementation supposed to have in that situation?
So in that particular circumstance, I believe it was concurrent read, concurrent write. As long as you have a priority of making that happen in the stack, that's sort of an algorithm detail. The scheduler's job is just to make that data available to the algorithm to work with. So the scheduler says, okay, I'm going to write this thing out to the global memory, and then people can read it from somewhere. And they can put their data back in as the algorithm says.
But in the meantime, I'm still working on the same data, right? Like in my local stack, possibly. These changes have to be merged at some point, right?
So the stack data for B is never going to get to the heap if you're working on B right now. You could end up making changes to the data from A in the heap. And I don't think we discussed the serialization of that. But if your algorithm is an effective fork join algorithm, it's going to make sure that it doesn't have those data race conditions in the algorithm itself. So the scheduler does not fix data race conditions for you. That's the algorithm's job.
Okay, but in particular, there's no properties that you're guaranteeing it has with respect to how it... So you just assume that no processors ever try to write to the same data. Otherwise, there's no guarantees about what it...
So we assume that the application handles all of the concurrency issues it generates. And our guarantee is that we're not generating additional concurrency issues beyond the application. Was there a question in the back?
Yeah. Do you have an example, or have you worked out how your fix is going to fix the topological example that you have in the previous slide? And also, do you have a slide maybe in the future that tells us how the DAG, the double and the Q, that actually got stolen in this case? Like how does that DAG evolves over time?
Right. So I don't have a slide that explicitly does this, but we can walk through this pathological example using the transformation.
Right. That will be
so first, we have root. Root gets to its fork. So it creates a forker task. Do we have any markers? Excellent. So we start with the root task. The root task forks into A and B. And we have the original DAG up on the slide there, so I'm not going to redraw that. So that becomes a dummy task. We'll call this dummy root. And forker root. Forker root goes and creates tasks A and B. Everyone with me so far? We've applied the transformation once. So now A is running along. A calls fork. So A uses the same transformation to have forker A create, C and D. Because we've already seen B. So then C doesn't call any forks. So the processor completes on C. It goes to the thing on the bottom of its deck, which is D. It starts working on D. Assuming the processor is like me, it runs out of room at the bottom of the whiteboard and starts over on top. So D.
Getting invisible over there. Maybe you need to.
Maybe red would be a better color.
Get a red one. The red one looks better. At least the person who was using it had better luck.
All right. So we've got D. Is this better? Yeah. Excellent. So D forks, and it creates dummy D and forker D. And forker D creates F and E. And then we finish running E. E does not have any forks, so we go back to the next thing on the bottom of the deck, which is now F. F, continuing our pattern that gives us the long bad example we care about, creates dummy D. Dummy F, excuse me, yes, thank you. You can tell that I'm getting tired of writing these dummies and forkers. And forker F. And then forker F creates G and H. So this is the state of our deck. And then we have a whole bunch of processors who all decide to come along and steal from this process. So proc2 comes along and it says, OK, I'm going to take that thing, because that's at the top of your deck. So we write out this stuff. We wrote out 2 nodes worth of information.
When you say we, that's the initial processor?
Yeah, so processor 1 writes out this. Question?
So the energy budget, is it per processor or total?
The energy cost is total.
Okay.
All right. Am I good to continue with the example? All right, so processor 2 comes in and steals this thing. Processor 3 comes in, and it gets to steal B. So now it needs B, forker root, and root, but we've already written out root and dummy root. So now we only have to write out this thing. Proc 4 comes in, and it steals dummy A.
Which it seems like we're still writing out all the things that we had to originally.
We are, but we're doing much less per unit steal. And we can bound the total number of steals that we do. Whereas in the old model, you could do all of this in one steal.
So what's wrong with that? If you're saying you charge the total cost of the whole thing.
So what's wrong with this
the same.
is that we don't have an easy guarantee that they're not all like this. And it's probably possible to go ahead and prove one. But
even if they're all like this, what's the problem? We're spending the same amount of energy.
So we can bound the number of steals. Regardless of whether we're in this model or this model, we have the same bound for the number of steals. In this model, every steal can take up to ON. In this model, every steal can take up to O1. So if you have ON steals, or I forget what the exact number is, it'll be on the slides in a second. So
what are we optimizing? We're optimizing the total amount of energy spent?
Yes, we're optimizing the total cost of the algorithm using the cost bounds earlier.
So cost means energy spent, which is...
That is one possible method, yes.
So so it seems to be the same number of writes.
But he's saying the way he proves it is by having this bound.
Right, so the way that the work stealing scheduling proof works is it says we can do at most this number of steals. And for them, it's fairly trivial to say each steal has at most this cost. And then that leads to the fact that your total amount of cost for the system, whether that's energy or something else, is OW over P plus D. Here, we can't make the same assumption that things don't have a big cost when we're in this model. So we're doing a slight transformation to this, which doesn't save you any actual work, but it makes proving that you're doing that amount of work much easier. All right, question?
I guess I'm just confused because it seems like this would up the number of potential steals by n and then just kill the factor of n that you're supposed to be saving for a stable work.
So I'll show you why it doesn't cost us as soon as I finish proving that it works. Did you have a question?
Yeah, I guess I'm just a little confused. Is this then give you some amortized statement about like the original where you do this, or it doesn't?
So with this, you can have this purple box extend arbitrarily far down the line. With this, your box is going to end after at most 3 length.
If you have n steals, in this case, that's n times 3 writes, and in that case, that might be n squared. So that will be a big difference, because in that case, you need to write n things in the main memory.
I guess that's the question. You don't get some amortized result.
We have not found one for this yet. It is almost definitely possible by virtue of the fact that we can do this. But we do not have a proof that says the amortized cost of a steal in this model is 1.
And if there were such a proof, this would be basically not much use.
Is the proof
So yes, if you came up with a different proof that says the amortized cost of a steal in this model is 1, then you can skip this entire transformation.
Okay.
Unfortunately, we weren't smart enough to do that.
Okay.
Which leads to me standing in a room taking a whole bunch of questions on it that are hopefully helping you guys figure this out.
So you tried and you couldn't do it, or you just saw how to do it this way, so like why bother to try to do that?
So I personally did not find a way to do this. I can't speak for everyone in the group whether they put a lot of effort into it or not, since we spent a lot of time thinking about it individually.
How about we take the rest of the questions offline and let Charlie get on?
All right. So, running through the remainder of this example. This is proc 4, this is proc 5, this is proc 6, this is proc 7, and this is proc 8. And then you're out of things to steal. You'll notice that any of these circles, even in this worst case example, have at most length 3. And that's what we needed. Because we can now say that every steal takes a constant amount of writes and then therefore has total cost O of omega. So using that bound, we can then apply the original work stealing analysis to say that our cost is O of W over P plus omega D. The simple thing we're doing here is instead of using D in the original analysis, we're plugging in some new D prime to the original analysis, where D prime is the depth of our transformed graph. And the depth of this graph can be at most 2 times the depth of the original graph here. Because even if every single node you have in here is doing a no-op, you're still only creating twice as many nodes. Question? No, okay, you're just playing with the 4. Okay. So this is great because it gives us the same asymptotic bound as the original work stealing, which is awesome. So, coming back to our example of why do we care. So, we've looked at reduce under the asymmetric PRAM model. Every single write has to go to memory. Your communication has to go directly to memory. With the asymmetric nested parallel model, if you assume that all the work is being done on one processor, then all the intermediate steps take place in that processor's stack memory, and you only have to write out the final answer. You end up doing O of 1 for a total cost of n plus omega, which is a lot better than n times omega. And your span is affected similarly. Now, it's possible that you're going to do this on a lot of processors, because maybe you have a gigantic data set. But we can now take that factor and say that that's part of the scheduling cost as opposed to part of the algorithm's cost. which is one of the main benefits of the nested parallel model that we've now moved to the asymmetric set. Any questions about the model? All right, so since I'm low on time, I'm going to breeze through tree contraction as our example of one of the ways we use the model. So currently, if you want to do tree contraction, you essentially compress the tree by raking in the leaves and compressing chains. Is everyone relatively familiar with that concept? Does anyone need more explanation there? All right, awesome.
I thought questions weren't allowed anymore.
He can't ask us questions, is that what you mean?
Yeah, well, right.
All right, so again, this has the thing where you have to communicate between processors explicitly, and you have to write everything out to the heap. So you have an omega factor on your work here that we would like to get rid of. So what we're going to do is we're going to first assume that our stack memory is big enough to hold about omega things in it. And then we're going to divide up our tree into some lovely artistic partitions. And we're going to say that those partitions are of size omega, so that they fit in our memory, and we have n over omega of them. Then we're going to sequentially contract each component inside our stack memory, so that doesn't cost us any writes. And then we have this wonderfully blobby looking tree that's of size n over omega. And if we call a regular tree contraction algorithm on this, it'll do n over omega writes because it's a tree of size n over omega. So you have omega times n over omega in your cost for just cost of n. So now, assuming that you're all curious about the tree partitioning algorithm, I'm going to tell you about it. So classic tree partitioning, you follow the Euler-Tor, which is essentially you start at the root, you go left as long as you can, then you go right once you're done going left, and then you go back up. And you generate the subtree sizes here. You find the m critical points, and then you partition the tree where each m critical point starts a new partition. So rather than using the m critical points, we're going to pick some different points for our partitioning. Because in order to do this, you need to write down the size of each subtree. And that's a write for each element in the tree, which is O of n writes. So for our partitioning, we're going to mark each node with probability 1 over omega. So each node flips a coin. All the nodes that flip heads mark themselves. Then we're going to traverse the Euler-Tor along the paths here, starting at each of these nodes and the root. And we're going to mark every omega node, which is going to give us some paths of length at most omega. Then every node that we've marked in these first two steps is going to pair off and mark the highest nodes between them. So you follow the Euler-Tor from the first node to the second node, and you mark the highest node you encounter along the way. Each of these steps can be done in a constant number of writes per chunk, where a chunk is either a coin flip or a traversal from a marked point on the Euler-Tor to another marked point on the Euler-Tor. And all of these chunks can be done in parallel. So then, once you have all of these marks, each marked node starts a new component. And since we have marked n over omega nodes in each step here at most, we have O of n omega partitions of size O of omega. We can prove that they're size O of omega here by making use of our second step. So every given partition contains at most 3 paths in the second step. Because if you had something that was marked that was not, or excuse me, something that was marked in here, you would also have the thing between it marked, which means that this new path here that's generated by the new marked node would be in a different partition. So that's the proof of why the partitions are the appropriate size. It's very rushed, and I apologize for that. But using that, we can now get our partitions sequentially contract them, and use the resulting supernodes to run a symmetric algorithm and only pay omega for each of the n over omega nodes in our new contracted tree, which gives us, once again, our additive factor of omega to the cost instead of multiple. So here, in summary, we've created a great new model for asymmetric algorithms, or algorithms on our new wave of asymmetric memory technologies that helps us model these things, it helps us schedule these things, it does a lot of great stuff. It also leads to a lot of questions, which is good. And then we've designed some algorithms. I talked about tree contraction briefly. There's a whole bunch more of them. Hopefully you're all as interested in that as you are in the model itself, and come either read the paper or talk to me offline. Thank you very much for listening.
I thought that the co-author worked out the problem of computing the m critical points. You could truthfully do a very simple version of that. You just compute those critical points, the m critical points up front. I think we worked that out, right, the other day? Did you check that?
Well, I don't think that will work. I guess that's our conclusion at that time. We were just confused.
Okay.
Maybe we should talk more about that offline.
It's trivial to do that, just do the n critical points.
All right. It's certainly possible.
So do you have a clear, like, best algorithmic open problem in this model? Can you do something like one of these spanning tree, or is there one of these that really, like, the one that seems like the best problem?
So, open problems at this point, we're still searching for problems where it's not either trivial or extremely difficult to prove bounds that are different from the symmetric setting. But we are working on doing some experimental implementation of these algorithms to verify that the asymptotic performance is indeed beneficial in the real world. And that's sort of where our research has been focused right now.
The spanning tree actually is the only one on this list that isn't tight, like according to the very trivial, you have to write out your output.
Any more questions?
Do you have at the moment? Do you have any idea of how big omega might be in practice? Like, is it like around 10? Is it around like 1,000?
So depending on whether you care about energy, bandwidth, or latency, we've seen omegas that range from like 20 to a couple hundred.
Thank the speaker again.